I bought this robot at an auction for about $100 just because I thought it looked cool and it might make a fun project restoring it. And really, I know almost nothing about it at the time that I got it. This company, Nomadic Technologies, was bought out and stopped manufacturing robots around the year 2000 or so. So this thing was probably built in the late 90s, if I had to guess. They made a few different models, all kind of somewhat similar looking to this one, which it seems were mostly sold to researchers who were studying like exploration algorithms and mapping of rooms and things like that. And I haven't found very much information on the internet about these because the company's original website, if it ever existed, is long gone. No owner's manual, operation manual, schematics, anything like that. I think it's a model N150 or maybe N200, just based on the Googling that I was able to do. I have no documentation with it or any other info. It's in a non-working condition. The two switches on the top, neither does anything. It's labeled console, joystick. I do not have a console or a joystick. The only artifact of Nomadic Technologies that I managed to really find was this little page with a very similar looking robot that doesn't have that much info and seems to not have been updated since 2004, but it had a little bit of stuff about some of the original Linux code. And then I also found this ancient Georgia Tech website that was probably written during the Civil War, which had a few pictures of some very similar robots. I think that one's an N200. That one, I don't know. It is different from what I have with wheels on the outside there, but it looks like it's solving some kind of maze. These, I think, are the same model that I've got, the N150. I noticed they've got this big, I don't know what, on top. Mine did not come with anything like that, and I also don't know what this is, but it seems to be pretty similar. And it's quite dusty and seems to be missing a few parts, so I can only assume that it's been just sitting in a warehouse or something for a while. On top, it's missing probably some type of connector here that aligns with an unused connector on the PCB in there. This upper turret assembly rotates relative to the body, and it seems to be driven by a spur gear there. Around the ring, there are a bunch of ultrasonic sonar modules. Each one has what appears to be a green and a red light. And the lower skirt is on these drawer slide type of mechanisms that allow it to lift up only so far relative to the body. Also, there appears to be some type of antenna over here next to these two handles, I guess. The undercarriage has 3 wheels, each of which is driven by this bevel gear assembly. And all the wheels have a big chunk, a big flat spot missing out of them. So I assume it might have just been pushed along sideways at some point. These are not easy to back drive. Also, the 3 wheel hub assemblies rotate in sync with each other, independently of the rotation of the body. So that must be how it steers. There seems to be a single large DC brushed motor right there, which I'm assuming is the drive motor that actually spins the wheels. There's 2 of what appear to be the same smaller DC brushed motor there and there, and they do actually seem to have a few extra wire connections coming out of them, so maybe rotary encoder for position or speed measurement, but I would assume those are for one for this rotation and one for the turret rotation. There are 3 PCBs around the perimeter, one next to each wheel, that appears to be the same. And there's a larger couple of stacked PCBs, all connectorized in the center. There's also a 2-pin connector and an empty clip, 3 of them around the perimeter. So maybe those are where the batteries used to go at some point. Most of the body panels seem to be anodized aluminum, if I had to guess. And that is all that I can really tell about this robot from the outside, so I'm gonna start disassembling it and just see what I can figure out. Just pop the hood, and every single one of these sonars has its own PCB with a ribbon cable coming into this main central PCB. There's some kind of radio unit under here. That's the e-stop button, what I assume is normally the on-off switch, and a few connectors on top. Every single one of these PCBs is labeled made in the USA, which is kind of interesting. You don't see that much anymore. This one's labeled power distribution board. And at a first glance, this main PCB, it's kind of unusual to see chips like that on most of what I'm used to, which is 20 years newer than this. And it seems like it has an extra little prototyping area, maybe, with a bunch of through-hole solder pads, a few resistors, and some switches. I'm filming everything I disconnect mainly for my own later reference. This wire is labeled SER, and it goes to the radio. This wire also goes to the radio, unlabeled. So with the top taken off, this port labeled debugger and this reset switch are what was accessible through that hole in the top. All of these connectors around the perimeter were totally unused, so maybe they just reused the same board for a couple of their other robots and it does something there. Each of the sonar PCBs has a 10 position ribbon cable going to it, and those two lights on the front are connected to LEDs on the other side here. I would assume these resistors are current limiting resistors for the LEDs. And then there are only 2 wires going to the front portion of each of the sonar modules. I see some handwritten stickers on a few of these chips. I assume that's maybe version number of software that's flashed onto them. I do notice it contains N150, which I think is the model number of this robot. The main board is labeled Intellisys 175 Rev 3. It's kind of neat that they anodized this entire plate red. Just kind of not sure why they went to the trouble. I just went around and labeled the top of each connector to match what's printed on the PCB down below, and number 16 is under this large ribbon cable. So there are 16 total sonar modules labeled 11 through 27. The sonar board popped out of its standoffs pretty easily. Of course, there's a nice healthy mixture of both standard and metric fasteners on the same part. This sticker fell off of that chip, and look at that. There's actually a transparent portion of it. I've never seen that before. Taking this clip for reference before I disconnect these 3 of the same connectors so I don't plug them back in wrong. And then the last thing holding this board in appears to be the large connector labeled slip ring. With the main board out, I can see there appears to be some hand-done modifications on the underside. That's where that little switch box was. And the only wires that appear to penetrate below this plate are the ones coming from the slip ring connector and what I assume are the main power cables. So I took off the sonar housing, and there's a couple of interesting things here. So it was bolted both to this outer piece and to this inner piece. Without the sonar housing bolted down, these two can rotate independently, but in practice, they're bolted to the same part, so they must move together. This is the slip ring for the power cables, these two here. I don't know yet what's going on with this, but there's just 2 big brushes on some springs that are kept in contact with those rings as this turns. And I was expecting like a Lazy Susan style thrust bearing for this big outer part, but actually it has a pretty sharp edge there and these V-shaped bearing profiles. They're not adjustable in their position, and none of them are sprung, which makes me think they must be mounted on eccentric nuts to set the preload correctly. I do see what I think is a sprocket for a timing belt that moves with the slip ring, and it's on a slot, so I assume that's to set the tension in a belt. And another of these blade style sensors on the edge. I assume that kind of acts like a limit switch to set the zero, like to home it. I think these are literally just drawer slides, but this seems to be the end of their travel, so I'm trying to figure out how to remove the skirt all the way off. Usually drawer slides would have a little release lever near one of these interfaces, but I'm not seeing that anywhere on these. So after removing the two lower screws on each of the slides, I was able to lift the entire skirt off the top. Also, there's the bumper interface board. So there's quite a few wires going into the two outer rings here, so there must be a ring of sensors around it. Also, this outer section is thin aluminum. You can see the weld seam right there, kind of cool. I guess it was made with a ring roller, maybe? Now that the skirt's out of the way, I can see a little bit more clearly. This DC motor has an integrated gearbox on top, and then drives a pair of spur gears with a pretty high reduction ratio up into this timing belt. That pulley right there is the tensioner, which is mounted into a slot to set the belt tension. And this other one on the right is just an idler. So this motor spins the slip ring in the center and thereby the turret on top. So the large DC motor looks like it has a small planetary gearbox, and then it drives this smaller timing belt, which goes through lots of these tensioner pulleys, and these larger pulleys are what actually drives the shafts that the bevel gear is fixed to. So that timing belt wraps around to all three wheels, driven by the same motor, to actually spin the drive wheels. So that means that all three drive wheels are mechanically locked in phase with each other. So if one spins, the other two must spin at the same speed. They cannot ever spin at different speeds, so it only steers via this rotation. It can't do like a differential thrust, so to speak. And for the steering rotation of the wheels, the entire hub assembly actually rotates. Note that the bevel gear does not rotate with it. And there's a thrust bearing there because this is actually taking the entire weight of the robot. And so the steering motion is controlled by this wider timing belt. And so the drive and the steering pulleys are coaxial, with the drive pulley fixed to the inner shaft that drives the bevel gear, and the steering pulley fixed to the outer shaft, which rotates the hub. So notice how I spin one but not the other, even though they're on the same shaft. This is the steering motor. It appears to be the same part as the turret rotation motor, and it goes through the same type of spur gear reduction. It's only connected to the motor that drives it, and it's fixed to this shaft along with that timing pulley for the steering timing belt. So all of the wires for the upper portion pass through the slip ring, except for these extra power wires and the wire for this sensor. And that's because those are fixed to this plate, which does not rotate relative to the rest of the turret, or rather does not rotate relative to the rest of the main body. Those wires all come out that access hole. This is the one for the bumper sensors on the outside. But then deep in the center there is the portion of the slip ring, which allows the larger bundle of multicolored wires to rotate. I don't really have any reason to disassemble this midsection with the belts, pulleys, and gears. They all seem to be running fairly smoothly, and the belts seem to be in good condition. So I'm gonna leave that alone, but I do want some better access to this area. So when I flip it over, I'm gonna put it on some wood blocks on this ring just to make sure that I don't pinch the wires right there. So I've got it resting on blocks, and I want to take this plate off so that I can access all the electronics in there. This robot is held together. The structure of it is with these big standoffs between all these plates. I removed all the standoff screws and the brackets which held the drawer slides, and this plate seems to be free now, but these PCBs are fixed to it, and I'll have to see what may need to be disconnected from the center also. I marked these PCBs 1, 2, and 3 with the standoff near where they came from before I remove them. And the first thing that hits when I try to remove the whole assembly is these connectors on the end of the motor right there. So I'm gonna pull these two off. The next thing to get caught is that bundle of wires that does not go through the slip ring. The wires getting caught on the bottom were this guy and this guy, neither of which are connected to anything. So I can hopefully just snake those down through this hole. The other one is this guy, which I can easily unplug from that sensor. The annoying one is that the two wires going to the actual brushes on the slip ring up here are included in that. So that pulled out easily, and I sharpied this one with a plus because actually both sides are black, so that way I won't forget. So of the 6 power wires coming through that hole, the 2 single pins went to the brushes on the upper slip ring. And then here's a clue. One of these is labeled 24 volt and one 12. So I assume these might have just been kind of auxiliary power outputs for add-on sensors or whatever. I don't know what the battery voltage is supposed to be, but this kind of makes me think it's 24. Next thing that limits me, the power wires from this motor, which are pretty easy to pull off. And then these extra ones, which I think are probably a rotary encoder. And next is this large bundle of small wires coming from the lower slip ring. And I'm gonna be really careful with this one because I really don't wanna break those. That'll be a pain to solder back together and an absolute nightmare if it breaks there. Sneaking those power wires through. The electronics are now finally separated from the mechanicals. These motor control boards all seem to be the same at a glance. I Sharpie labeled them according to which motor they were plugged into. And I notice someone wrote 13A on the bottom of that, perhaps 13 amps. The one connected to the turret is labeled 5A, maybe 5 amps. And the last one for steering is labeled 4.5A. So that roughly corresponds to the current draw I would expect for motors of that size. All of these boards are labeled servo amp, except the turret one where it's partially crossed out for some reason. I'm not totally sure why I would say servo amp. I'm pretty certain that all 3 of these motors are brushed DC motors, but maybe with the rotary encoders coming off of them, they're kind of behaving like servos. This motor says 24 volt on it, so that agrees with my suspicion that the battery system should be 24 volt. January of 1998 manufacture date it looks like, so good 25 years old. And here's the label on the drive motor. This one is a youngster. It's not quite 25 years old. And it is also 24 volt DC. Here's a look at that 24 pin slip ring. So the drive control for this entire robot boils down to 3 DC motors. One for actual driving the wheels, one for steering, and one for turret rotation, which isn't really that important to driving. These 3 connectors, which were not hooked up to anything and just kind of floating around down here in the bottom of the robot. So I'm assuming that these little 90-degree brackets used to be what held 3 batteries in place here for each of these. The 12 volt connector comes from this upper PCB here, whereas the 24 volt is routed right into one of the same connectors, number 17, that I think used to go to a battery. So that strongly suggests a 24 volt battery system is what this was intended for. The 24 volt connector, actually its positive line goes to one battery connector and its negative line goes to another. And these two also have a blue wire running between them. So these batteries may have been in series to 12 volts to make a 24 volt. And the other reason I think that is because the third battery, number 18, only has 2 positive negative wires coming out of it. It's not in series or parallel with anything else. So it seems like it actually has a separate 12 volt and 24 volt system. The labeled 12 volt connector appears to be in parallel with the 2 that went up to the main power slip ring in the turret. So probably everything up there is getting 12 volts, while the motors, I believe, are getting 24. The lower board is labeled relay board, and the upper one is labeled slip ring board. The plot thickens. This 3-point connector is labeled 24 volt, 5 volt, and ground. So all signs point towards a dual system, 3 12 volt batteries with 2 in series and 1 on its own. Each of these drive boards has this 3-pin power connector coming from the central boards, and it has the 2 DC power connections going out to the motor, and then it has this 5-pin communication cable running between the motor control board and the central board. There is one unused connector at the top. Through this janky arrangement of alligator clips, I'm providing 24 volt and 5 volt onto that 3-pin connector down there. The top one's ground, middle one's 5 volt, bottom one's 24 volt. And the reason I've got so many alligator clips going on is because I'm also taking that 5 volt source to this breadboard where I've got an Arduino Pro Mini, and I'm feeding 5 volt and ground into this connector. I kind of beeped out the board before I started plugging stuff in and determined that the pins labeled ground and 5 volt on this are not shorted to the ground and 5 volt pins over here. And first I just powered this big 3-pin, and I was not getting 5 volts over here. So once I fed that 5 volts, 24 volt to the main power connector, also 5 volt to that middle pin, I got these red LEDs to come on. So that's the only sign of life so far. The Arduino is not actually doing anything right now. The other 3 pins it's connected to are PWM, DIR, and CL. So right now these are all just kind of floating and it's not doing anything. Now I'm feeding both the DIR pin and the CL pin just a digital high, and the PWM pin a 100% duty cycle from the analog write function. And now on the back, I got 2 green lights. I measured the voltage on the motor output. That's the connector that goes to the motor output, and I was getting 24 volts out of that. So if there was a motor plugged in right now, it would probably be spinning. Very exciting. First real signs of life. This is just a random little DC motor I had laying around that I hooked up for testing. It's just plugged into the normal motor connector there. And now I've got the Arduino alternating between a digital high and a digital low on the direction pin, feeding the PWM a constant value of around a 20% duty cycle. Just because I don't think this motor's intended for 24 volts, I wanted to keep it pretty low. But you can see that it is changing direction every 5 seconds as programmed. So it seems that this motor controller works, and I'll pretty easily be able to hijack it using only a few of these pins right here. One more thing I've noticed is that this second green LED turns off every time the motor changes direction. So that must be linked to the DIR pin. I've yet to see the yellow lights come on, and the red lights have been on this entire time. So I beeped out the whole pin out for this 24 pin slip ring connector, and I found that all these pins go to either the 3 motor controller connectors, the motor encoder connectors, a few go to this turret and base connector. Also several go to this bumper connector over here. One of them goes to one of these terminal blocks, number 7. If I apply 12 volts to it, you can hear that relay clicking. It's this relay right here. Pause the video if you actually need the pin out for some reason, but this is the big 24 pin slip ring. This is the motor control header on the triangle PCB, and all the other smaller headers numbered in the same way with the same notch on this side, like the bumper, turret, base ones. They all had pins 1 and 2 as ground, 5 volt. So I got 3 new batteries, all of them these ones. I chose this one because it's nominal 12 volt, which is what I need. It's exactly the right dimensions to fit perfectly within the existing slots, as well as the height between the platforms. It has a max continuous output current of 20 amps, which is plenty for this, and it has an internal BMS, so that'll protect me from over discharge. I have no idea what batteries this actually would have had originally. Probably sealed lead acid, given that it's from the 90s. So in this case, I should have actually a lot more capacity than before. And I just ended up swapping the connector for an XT60 there, and added some 1/4 inch spade terminals to go into the battery. Now I've got all 3 batteries installed on the base tray, and I notice as soon as they're plugged in, these little LEDs down in the corners, I don't know if you can tell, just lights up very dimly, I guess to indicate that a battery is connected. Also, the labeled 12 volt and the 24 volt auxiliary outputs are both hot now, checked with a multimeter. 12 volt is at battery voltage, which is like 13.2, and the 24 volts at about 26 something, 2 of them in series. And so if I take a jumper from pin 7 on the slip ring connector header, like I showed before, and I jump that straight to the positive of the 12 volt, we get relays clicking and lights coming on all 3 motor drivers. So that's good. Looks like all 3 motor drivers are getting power. and the power distribution is working as expected. Also, the two large slip ring connectors are hot with 13 volt battery voltage as soon as the batteries are plugged in, so I can use that to power a microcontroller up top. So now I've got an Arduino Uno running off the battery power, which is coming out of the slip ring connections, and that is outputting its 3 signals directly into the header for the 24-pin slip ring. And now that is running one of the motors off of all its original hardware, the controller and the central connection hub and power distribution. So now we have 3 motors running simultaneously on all 3 drivers, just to test that they all work and I can control them all independently. I wired in an old PS2 controller, rather a knockoff PS2 controller, and I chose that over the Xbox 360 because it turns out these things, you can read them just from an SPI port, whereas the Xbox 360 controller needs a USB host, and there wasn't a good pre-existing library to figure that out easily, so I went with this. I cut off the original plug and spliced in this DB15 connector. So there are a lot of unused wires. The PlayStation controller only needs 9. And I have that plugged into the existing female port that says joystick. The back of that goes to this 16-pin ribbon cable, and I just have the necessary ones for the PlayStation controller going to my Arduino. I don't have all 9 because I'm leaving out the vibration motors and stuff, but it's basically just using an SPI port, and I definitely needed these 1K pull-up resistors to get that to work reliably, probably just because the cable is so long. And I know I keep switching microcontrollers around in this video, but the reason I went with the Teensy 4.0 is because this uses 3 volt logic level for the controller. Now that I'm able to get good analog readings off the joysticks and also all the buttons, all I need to do is just make a relatively simple program that translates that into PWM signals for the motor drivers on the actual robot. Got all my batteries mounted and all the electronics plugged back in. The new batteries are pretty tight in those slots, a little too tight to remove them without undoing those screws, but I can pretty easily access that connector to charge them without removing them, so that's okay. And I've got it more or less assembled up on blocks, just so I can test the wheels and everything. I'm about ready to plug the Arduino back in and try powering on the motors. While setting up my Arduino, I accidentally touched these 2 alligator clips together and shorted, and I believe I blew a fuse because now I'm getting no voltage across here, which should be the 12 volt battery voltage. So I did notice there's a fuse for each battery back in there. I'm also noticing that this LED is no longer on, so I assume that's the fuse that blew. Here's the original fuse. It is definitely blown. I checked it, but the only ones I have on hand are not the right form factor. It's the same amp rating though, so I just kind of jammed it in there and we're gonna roll with that for now. So I'm just having the Arduino adjust the motor driver to a set predetermined value one at a time. And here goes the drive motor, 25%. And here's a steering motor test. This is 15%. And last but not least, the turret motor. when it's actually fully assembled, everything above the slip rings will be rotating with the turret, so I won't need to worry about any of these wires getting tangled up. Here's what the belt moving with the turret motor looks like. And here's both the steering and the drive operating simultaneously. Okay, this is going to be just the drive motor accelerating slowly up to 100% speed. Now this will be just the steering motor at 100% speed. And now, just because I cannot resist, here's both steering and drive at 100% throttle. This thing's honestly kind of scary. So I'll probably stick with the Teensy 4.0 just because its logic level works nicely with the PlayStation controller, and I can make it work with the existing motor drivers. It definitely doesn't have enough pins when I eventually want to get all the sonar modules and all the other lights and stuff working, but it should be more than sufficient for just playing with the drive control for now. Now I'm mapping the up and down on the left stick to the drive motor, the left and right on the left stick to the steering motor, and the left and right on the right stick to the turret motor. And I have it set to where if it loses connection from the controller, it'll just put all the throttle to 0. All right, so now I can drive and steer with just one finger. Pretty cool. This is a lot clearer now that I can adjust these values by hand instead of just typing things in. But those green LEDs, the brightness actually is correlated to the throttle of the motor, so it must be wired into the PWM signal. You can tell it just barely lights if I barely tap the stick, and then it gets real bright at full throttle. And also the other one only comes on when you change directions. So kind of just now fully figured out what these lights mean. So because that central shaft with the bevel gear is fixed when I only turn the steering motor, the wheel itself will actually rotate a small amount forward and backward. I could write some code to compensate for that if I did the math with all the gear ratios, or I could just not do that. So I got the upper part of the turret reassembled, just kind of taped down all the connectors for the sonar modules that I'm not gonna hook up just yet, but I definitely want to in the future. This is 12 volt coming from through the slip ring, and I think I'm just gonna use the original power distribution board. I can plug that right in, and it's a bunch of 12 volt connections in parallel, so I can run one up through the switch on top that'll just plug and play, and then that'll power the Arduino, which will live somewhere in here, and I can also route in the existing e-stop button. Here's the finished proto board that I just soldered together for this. It mounts the Teensy 4.0. This big 24 pin header with all the white wires is for the slip ring connector on the robot. The yellow one is just taking a 12 volt that I'm running through the e-stop to power that pin 7, which energizes the relays on the bottom in that triangular PCB. So over here, this 2-pin connector, that's where I'm putting my 12 volt power input. And so that 12 volt signal comes off of that through this 3-pin header, which is just the e-stop. Only 2 pins of it are connected through that switch. And then this is a DC-DC converter to step that that 12 volt down to 5 so it can power the Teensy. Then over here, the 16-pin header, that is for the connector that goes to the harness for the PS2 controller. So all the green wires are the data connections for that, the SPI, and then the blue is my 3.3 volt, which goes to all these pull-up resistors. And I just plugged it into the actual robot to test, and everything does work. So I'm gonna make a nicer mount to hold it in here securely. But the basic layout is this 3-pin header over here goes up to the 2 wires going to the original e-stop button. Just cut that harness and spliced it in. Same kind of deal with the 2-pin header. Goes to this 2-conductor cable, which is spliced into one of the original wires coming off this power distribution board. This one is just a ground to the chassis, and the other one that's plugged in over here goes up into the existing harness for the original switch. And that lights up when it's turned on and off. And then after it goes through the switch, that's where the power comes up and out of the power slip ring. So that switch basically cuts power on and off to this entire distribution board. Then I've got the 24-pin slip ring harness plugged in there, and this ribbon cable goes to where my controller is plugged in on the outside of here. So having the e-stop routed this way allows me to completely cut power to all the motor drivers and immediately stop the motors, while allowing the microcontroller to still be on and running. And there's a couple advantages to that. One is that I can flash the code to it, and even if there's some bug or something, I don't have to worry about it immediately starting to drive on me, because I can control that power separately. And I don't have to worry about anything shorting or going wrong, software or otherwise, in that more delicate microcontroller proto board assembly, because the e-stop is just wired separately straight to the power source that energizes the relays that give power to the motors. All right, I got the top mounted, and we're going on our first test drive around the house. I printed this little adapter with some screwed in heat set inserts that will bolt my proto board into this top metal plate. So once it was all buttoned up and ready to drive, I figured logically the skate park was a great place to test this robot, meant for flat level ground. Here it goes off the first little slope I drove it on, and as soon as it started going down the hill, it just completely slid all the way, and there was no stopping it. it really doesn't do well on anything more than about a 10% grade. Also, you can tell on this little straightaway, but that periodic clicking and kind of oscillating sound is from the flat spots in the wheels. You'll notice me banging into the walls and kind of run it off the road a couple of times nearly here. The steering is kind of both squirrely and pretty unresponsive at the same time, but I was able to make it most of the way around this little track. Most of what makes the steering difficult is that when it's at a stop or a very slow speed and you start giving it a little bit of throttle, there's no visual indication at all for which way it's going to start driving because you can't see the drive wheels at all. And it doesn't have any kind of passive self-centering like a car steering wheel or a bicycle would, so any small change just rotates the direction that the wheels are facing, and then it just stays driving in that direction. So it takes a lot of constant little fine adjustments that you can't really see the effects of until it's kind of too late and you've overcorrected. But of course manual driving is not the point of this robot, and I will get into some autonomy soon, and especially once I have the extra control given by using the encoder data and everything, I think I'll be able to have the robot steer itself a lot better than I can steer it. This clip is the onboard camera, sped up 4x, and it was really doing okay going around the track, struggling a little bit here and there on the kind of extreme slopes and angle changes, and then unfortunately I managed to roll it over here in the next clip, and then that was the end of the track day.
Too bad they didn't get that on camera. Sorry. I made you lose your focus.
Yeah, dude. Oh no, I lost the battery. Yeah, not a good skateboarder. That's okay.
So I got it home. Here's the damage where she flipped during that little tumble. Trying to figure out what's wrong with it. The switch does still light up, so I'm at least getting 12 volts. And I can see the light on the microcontroller in there, so that's still on. Opening the e-stop, I hear the relays click at the bottom, so I think I'm probably getting 24 volt still. The controller was plugged in when it flipped, and I noticed this connector seems like it might be a little bit pushed in. And looking at this guy, I noticed that top left pin is definitely bent in, so maybe that's the culprit. Maybe I'm just not getting a controller signal. So I carefully bent that pin back with needle nose, and it actually works now. All three motors, so that's all it was. So this is definitely a weak point in the event of a rollover. These bars kind of seem to be high enough to protect the switch and the e-stop, but hopefully this thing never rolls over again. It's kind of meant for just flat ground, and I guess that's what I get for taking it to a skate park. So that's it for now on this guy. Upcoming plans for it is definitely I want to get all the sonar modules wired up and working, and their LEDs. Also the encoders for all 3 motors so that I can have better precision speed control and position control. There's a lot more potential for this robot once I get all those functioning. I also want to see if I can get this original radio to communicate somehow, because just running it on the PlayStation controller is kind of useful for a quick and dirty manual mode, but really I want this to be wireless and I want it to have some level of autonomy. So those are the upcoming plans, and thanks for watching.